Alright, in this video we're going to be talking about the introduction to gases. Alright, so we're going to go ahead, we are going to get started. So the overall idea and everything for this is that we are going to look over the gas properties, the temperature conversions, gas relationships, in order for us to really understand the conceptual idea of what a gas is and how it relates to pressure. So there are going to be a few different definitions that we are going to need to know first. So first is going to be the expansion and compressibility of gases. So gases have the ability to increase or decrease their volume depending on what container they are in. Now, the density of different gases is going to be the measurement of mass per unit of volume. So the closer those gas molecules are to each other, the denser it is. The larger space in between them, the less dense it is. Next is going to be our fluidity. So fluidity is going to be the ability of a substance to flow. So some gases have a really high fluidity to them, so they are able to flow very easily. This can be seen in weather patterns. So El Nino or any of those weather patterns where we have a airflow, that and everything is going to be the idea of a gas fluidity. Our next part is going to be our diffusion, which is going to be the movement of particles from a high concentration to a low concentration. So very similar to different particles in a solution, they are going to go from that kind of like high concentrated area to a low concentration. Another example of this would be the idea of Febreze. So if you spray Febreze into a corner of a room, eventually you'll be able to smell that throughout the entire room from it. And then our last one is going to be effusion, which is going to be the emission of something such as a liquid or gas from an opening. And typically, the smaller the opening, the faster the release is. Alright, and then next comes the kinetic molecular theory. So the kinetic molecular theory is going to be the idea behind all gases, and we assume that the majority of gases follow the kinetic molecular theory. So the first part is that gas particles are smaller than the space between them. There is no attraction or repulsion between gas particles. Gas particles will move in a constant straight line motion. Gas particles do not lose energy when they collide. And the kinetic energy of particles determines the temperature. Now, talking a little bit more about temperature, it is going to be the measure of the average kinetic energy of a system. So whenever we take the temperature of something, we are really taking an average kinetic energy measurement of the overall system. So whenever you take the temperature when you're sick, what you're really doing is that you're measuring that average kinetic energy of your body. Now, this is going to be important because all of our gas calculations are going to be done in Kelvin, not Celsius. So what we're going to need to do is that we are going to look on how to convert between our Celsius to Kelvin in order to perform different gas calculations. Our next part is going to be that the Kelvin temperature scale is based on the idea that there is a minimum temperature that can exist, and that minimal temperature is going to be called absolute zero, which is 0 Kelvin. So nothing can go below 0 Kelvin. So absolute zero is when there is zero kinetic energy in the system. Now, because of this, there are no negative numbers in the Kelvin scale, which makes it really easy to deal with. So our conversion factor that we are going to have for this is that 0 Kelvin is equal to negative 273 degrees Celsius. So we're going to be using this in order to convert between Kelvin to Celsius. So let's go ahead and take a look at a few examples. So our first one is 25 degrees Celsius. We want to go ahead and convert it to our Kelvin. So what we're going to do, because we are going from our Celsius to our Kelvin, we are going to go ahead and we are going to add 273 to this number. So what we're going to get is 298. And that will go right here. So 298 Kelvin is equal to 25 degrees Celsius. Now our next one is 195 degrees Celsius. Again, we're going to add in that 273 degrees, which will give us 468. All right, our next one is negative 40 degrees Celsius. Converting that to Kelvin, adding in 273 will give us 233. Our next one, 23 degrees Celsius. We add in that 273 to get us 296. And then our last Celsius to Kelvin, so 0 degrees Celsius, adding in the 273 to get us to Kelvin, it's just our 273. Now, taking a look at our last one, we're going to do the opposite. So we are going from 125 Kelvin, we want to convert it to Celsius, so we are going to subtract 273 from there. So we are going to go ahead 125 minus 273, and this will get us negative 148 degrees Celsius. And that is going to be how we convert from Celsius to Kelvin or from Kelvin to Celsius, is that we're just using that number 273 to convert between them. All right, now talking a little bit more about pressure. So pressure really has two different definitions that we're able to use for it. So the first one is that it is a physical force exerted on or against an object by something in contact with it. So if and everything you were to go up and start hitting on a wall, you're exerting a physical force on that wall and you're causing pressure to be exerted on the wall. Now, your pressure is going to be a measurement of the force of collisions between a gas molecule and the container, typically. So whenever you have compressed gas, so if we have oxygen gas and we have compressed it, what everything increases the pressure is going to be those collisions. So the more that a gas particle hits the wall of a container, the more pressure is being exerted on the container. And that is going to be how we really look at the idea of pressure, is the number of collisions. So the more collisions that we have, the higher the pressure is going to be. Now, we do have our different units for pressure. So we have our ATM, which will be atmospheres. So currently, if you're anywhere in the world, you're typically under 1 atmosphere of pressure because Earth has 1 atmosphere. There's also the mmHg, which will be millimeters of mercury. This is often used in weather. Your kPa, being kilopascals, typically used outside of the United States. And then our PSI, which most of us should be familiar with here in the United States, is being pounds per square inch. One of the most common areas for us to find our units of pressure for PSI are going to be on the car tires. So if your car tires are low in pressure, the side of your car will typically tell you what pressure or pounds per square inch that they need to be at. Now, we also have something called the standard temperature and pressure, or STP. So STP is going to be something that we use quite a bit throughout this entire idea of talking about gases. So it'll be our standard temperature and pressure. So our standard temperature is going to be 0 degrees Celsius, which is 273 Kelvin. Our standard pressure will be 1 atmosphere, or 101.2 kPa, which is also 760 mmHg, which is also 14.7 psi. So all of those are going to be the standard pressures that we use. Most often we are going to use the 1 atmosphere as our standard. Now, why these were set as the standard, especially for gases, because at these temperatures and pressures, the gases are going to act the most ideal. And it is a relatively high temperature and a low pressure. So we may not really think that 0 degrees Celsius is a high temperature, but we really need to compare this to the rest of the universe. So space, being mainly empty, is very, very cold. And so having a 0 degrees Celsius is actually a relatively high temperature when comparing it to outer space. In one atmosphere is also a fairly low pressure as well, especially when we take a look at the other planets in our solar system. So for example, Jupiter has an extremely high pressure of, I believe it's several hundred atmospheres of pressure. And so one atmosphere is a relatively low pressure when thinking about all of the other planets, even in our solar system. Now, we're going to talk about our gas relationships. And these and everything are just how we are going to look at pressure, temperature, and volume and how they relate to each other. Now, while in everything we go through this, we are going to assume that we are going to be dealing with an ideal gas. And an ideal gas is going to be a hypothetical gas whose molecules occupy negligible space, they have no interactions with each other, and they always obey the gas laws exactly. So we are kind of assuming that all gases are ideal in this in order to help simplify some of the calculations. Now, our first relationship that we are going to go ahead and talk about is going to be when we have a constant volume. So whenever we have constant volume, this will be known as Gay-Lussac's law. And that and everything will be when we have a constant volume. Now, how this looks on the chart is as I increase my temperature, my pressure will also increase. So as our temperature increases, so will our pressure, and vice versa. So if I decrease my temperature, my pressure will also go down. Now, what we should notice about this is that it is a direct relationship. And the reason that it is a direct relationship is because as one goes up, the other also goes up. So they're going to go up in the same way. Now, looking at everything at our next relationship, this is going to be when we hold the temperature constant, and this is going to be known as Boyle's law. So Boyle's law is going to be when we have a constant temperature. Now, the chart for this is that as I increase my volume, my pressure will decrease. So as I increase my volume, my pressure decreases. Now, thinking mathematically, as one thing increases and the other decreases, this is going to be known as an inverse relationship. So inverse, one goes up, the other goes down, and vice versa. All right, taking a look at our last relationship, this is going to be when we hold the pressure constant. So whenever we hold the pressure constant, this is going to be known as Charles' law. Now, with Charles' law and holding the constant pressure, as I increase the volume, my temperature will also increase, or vice versa. So again, as one goes up, the other also goes up. This will be a direct relationship.